Welcome to the California State Polytechnic University Pomona 2017 ASHRAE Student Design Competition HVAC System Selection. The design team is Edgar Barajas, Adam Reyes, and Farhang Razagi. Special thanks to our faculty advisor, Professor Kevin R. Anderson, and our industry advisor, Carlos Soria from Integral Group. Today on our presentation, we'll be introducing to you the executive summary and design parameters, ASHRAE standards, special systems, building model, HVAC systems, selection matrix, radiant heating, energy conservation methods, and approaching to net zero building and LEED. Design parameters. The Diego Ramirez Island is located south of Chile, close to the South Pole. The average temperature is 40.9 degrees Fahrenheit. The island has a relative humidity between 70 to 90% average year-round, which is relatively high. Yearly rainfall is 43 inches per year. Wind speeds are usually above 10 miles an hour year-round. This is a key factor in infiltration. The island has a good outdoor air quality because it is very remote. The owner required the building envelope to be based on ASHRAE 189.1. The design team also took further steps to improve the building envelope with the alternative systems. The exterior wall area is about 13,000 square feet and accounts for 18% of heat loss. From the Canadian Wood Council's wall assembly database, the following wall assembly was recommended. This assembly adds $3 per square foot to the construction cost, and it reduces the wall's heat loss by 32%. It improves ASHRAE 189.1 by about 100%. The owner specifies a number of indoor requirements. The building is occupied 24 hours a day, 7 days a week. The summer indoor design temperature is 73 degrees Fahrenheit dry bulb with a 55% relative humidity. The winter design temperature is 70 degrees Fahrenheit with dry bulb. The indoor noise requirement for the office administrative living space is noise criteria of 35. For the meteorological center, noise criteria of 30. The island also has sources of water, propane, and electrical rates. The project needs to comply with ASHRAE 15, ASHRAE 55, ASHRAE 62.1 and 62.2, ASHRAE 90.1, ASHRAE 189.1, and ASHRAE Fundamentals Handbook. Special systems. In cold climate, ensuring proper hot water supply system is crucial. ASHRAE Fundamentals Chapter 50 was referenced to calculate the size of equipment at 54 mph and 11 gallons per minute. The Smart 60 indirect water-to-water heat exchanger was selected for this job. The total lifecycle cost of the system is $15,000. Parking garage. Vehicles are typically run for 45 minutes twice a week in the parking garage and service stalls. The owner requires a separate exhaust system serving these areas. The design team chose an underfloor direct hose vehicle exhaust system. This system synergizes with the architecture because all exhaust ducts will be unseen underground. This also leaves extra space for occupants to use. Initial cost of the whole system is $1,740. Computer server room. The computer server room must be kept at 65 degrees Fahrenheit dry bulb, 50% relative humidity for 24 hours a day year-round. Tray 700 was utilized to calculate the cooling load of 2.7 tons and heating load of 12 mph. There must be strict control to maintain computer hardware operating conditions. A train impact package air handler is used to maintain the space at 65 degrees Fahrenheit. A carrier home dehumidifier is integrated with the supply ductwork to reduce moisture. During low humidity conditions, a carrier steam humidifier is used. Thermostat is used to control all equipment for excellent indoor air quality of the room. 2 pieces of each equipment is ordered for redundancy. The life cycle cost of this configuration is $41,000 over the building lifespan. The design goal was to minimize the number of zones for radiant floor heating. This allowed the design team to keep the number of manifolds down. A separate zoning layout was created for the air side to maintain excellent indoor quality and decrease energy consumption through a variable air volume design. Tray 700 was utilized to find the cooling and heating load for the building. Appropriate ASHRAE standards were applied to the model. A Diego Ramirez Island weather file supplied by ASHRAE was imported into Tray 700 and used for the load calculation. Libraries were created for the rate structures, occupancy, and building materials specified by the design parameters. The transfer function method was used for the heat load calculation because it was more in-depth than other methods. The radiant time series was used to find the cooling load because it considered to be the best fit method for this application. The cooling design day temperature is 53 degrees Fahrenheit dry bulb, 51 degrees wet bulb. Heating design day temperature, 24 degrees Fahrenheit dry bulb. The heating design day heat loss is 164.7 mph. For climate zone 6A, baseline system 3 was used with a direct expansion cooling coil and gas-fired heat exchanger for heating. The total equipment load is 394 mph. 3 HVAC systems were considered. 2-pipe hydronic fan coil with dedicated outdoor air system, variable refrigerant volume with dedicated outdoor air system, and radiant floor heating with variable air volume. First, the fan coil system supplies the majority of the heating load to the building. It is supplied by a hot water system. A dedicated outdoor air system brings outdoor air into the building. It is preconditioned by a steam coil and pre-cooled by a direct expansion coil. The total load for heating is 278, cooling 14.7. The variable refrigerant volume uses a dedicated outdoor air system to bring in outdoor air. The VRV indoor units do all the heating and cooling inside the building. The total load is 394 and cooling 18.1. For the radiant heating VAV bypass system, the radiant floor pads do all the heating in the building at 193 MBH. An air handler brings in outdoor air and humidifies the air to building specifications. The total load is 225. VAV bypass coupled with radiant floor. During the peak hour, outdoor air temperature is 24 degrees Fahrenheit. If sensible and latent heating loads are dealt separately, supply air can be reduced by 67% comparing to ASHRAE 90.1 baseline by minimizing outside air damper to 20%. During the hottest day, when outdoor air temperature is 54 degrees Fahrenheit, 20% of spaces such as conference rooms and bedrooms may experience some cooling load. Those cooling load can be handled by lowering the space surface temperature, resetting supply air temperature based on outdoor air temperature, and opening outside air damper to 40%. If the supply air and flow rate of cooling those spaces is greater than the zones that are on the heating mode, excess air is bypassed back into the system. Radiant floor heating VAV system is 57% more efficient from the baseline. In addition, the thermal losses associated with the forced air heating, such as leakage and duct insulation, are not affecting this alternative as much as other systems, since the air handling units are only responsible for minimum ventilation requirement and humidity control. Sensible loads of each space is met by controlled temperature surfaces. To fully monitor every space surface temperature, each heating panel is equipped with a sensor. According to ASHRAE 55, the major factors for a comfort zone are air temperature, mean radiant temperature, humidity, and metabolic rate of body. Radiant floor heating provides exceptional mean radiant temperature. Since the floor has a higher surface temperature of 80 to 89 degrees Fahrenheit for this project, mean radiant temperature in sample spaces such as the service stalls and bedroom were investigated during the peak day. First, surface temperature of all surfaces were defined. Second, the heating panel temperature was changed from 84 to 89 degrees Fahrenheit. The mean radiant temperature simulation suggested that by increasing the floor temperature by 5 degrees, set point for the service stall should be lowered to 66 degrees Fahrenheit to maximize occupant satisfaction to 80%. The mean radiant temperature simulation also suggested that for the small room such as bedroom that has an exposed wall, the set point should be increased to 78 degrees Fahrenheit, considering the occupant clothing and metabolic rate inside the bedroom. The radiant panel circuits were sized for 100% of sensible load. The loop CAD was utilized to calculate the heat loads. Then ventilation loads were imported from the Trace 500 to loop CAD. After the envelope's heat loads are confirmed between both models using ASHRAE 199.1 and also proposed R values, the design surface temperature for heating panels were set to 84 degrees Fahrenheit. However, the system is capable of increasing that temperature by 10 degrees Fahrenheit. Based on the manufacturer handbook Uponor radiant heating systems, the length of each loop was designed to not exceed 300 feet and within 2% across the manifold. Uponor suggests to control surface temperature by modulating the flow rate so that a fixed surface temperature is recommended. Appropriate tubes, manifolds, slabs, insulation, and actuators were selected based on the manufacturer guide. By analyzing the operative temperatures, the team found that if the heating panels are to be installed on the ceiling or the walls, the view factors of the radiating surface would affect thermal comfort. For the higher height spaces such as the service stalls, if the radiator surface is installed on the ceiling rather than the floor, then the operative temperature would predict to be within 80% of acceptability from ASHRAE 55 with using less energy. Median radiant temperature simulations suggested significant variance in operative temperature in the space that have one or more exposed walls. By installing the loops around exposed, thermal comfort in those spaces would be improved. Baseline has the highest energy usage intensity because it uses ASHRAE 90.1 minimum equipment efficiencies and energy recovery. Airflow is a constant volume, so the fan is always flowing constantly, unlike the other systems where they use VFDs. All alternative systems use more efficient equipment. Radiant system has the lowest EUI because heating load can be satisfied without cooling or heating the air, unlike the hydronic fan coils and variable refrigerant volume indoor units. Annual utility cost is highest for the baseline for the same reason that it has the highest EUI. Radiant consumes the least amount of energy because of the ventilation load required for the building, and therefore it has the lowest utility cost out of all the systems. A 50-year life cycle cost was done in all the systems. The baseline system had the lowest initial cost because it had minimum equipment to ventilate and cool and heat the building, but it had the largest 50-year life cycle cost at $2.3 million. Fan coils had a large initial cost because of all the equipment with the boilers, dedicated outdoor system, and the fan coils itself. Its lifecycle cost was 1.9 million. The variable refrigerant volume initial cost was 168,000. This is lower than the fan coils because it did not require boilers. Its lifecycle cost was 1.7 million. Radiant floor heating had one of the lowest initial costs at $174,000 and the lowest lifecycle cost at 1.4 million. This makes the radiant floor heating very appealing. The system selection matrix was created to rate the systems to see which would be the best fit for the owner. 9 categories were given. First, cost, operating cost, low environmental impact, synergy with architecture, reliability, flexibility, maintainability, sustainability, comfort, and health. Each category was given a weight from 1 to 5, 5 being the highest value, 1 being the lowest value. Each system was then scored from a scale of 1 to 5, 5 meeting all category requirements, 1 meeting no category requirements. After scoring the selection matrix, radiant heating VAV bypass scored the highest with a score of 122. Next was VRV with dedicated outdoor system with score 98. Third was hydronic fan coil with dedicated outdoor system with a score of 91. And lastly was a baseline with a score of 70. With its energy efficient equipment, excellent control of indoor comfort, easy integration with renewable energy, and low lifecycle costs, it is easy to see why radiant floor heating with VAV bypass is the ideal system for this project. Not only is the initial cost comparable to the baseline system, it is also a very low environmental impact. Energy conservation methods. Phase-changing material windows work by absorbing sensible heat when it melts and releasing latent heat back into the space when it solidifies. This is useful in our building because it absorbs the sun's heat and releases it into the building when the sun goes down. With a 311 square feet of window area, the building can save 605 therms per year, which translates into life cycle energy savings of $18,000 and 3 tons of CO2 per year. Although the total life cycle cost is $36,000, the main goal of these windows would be to reduce environmental impact. The owner requested to analyze the feasibility of photovoltaic cells. High-efficiency LG Neon 2 72-cell module cells were considered. System advisor model was used to analyze the system. Total module area is 10,882 square feet. Annual net savings is $3,000 with a payback period of 19 years. Highest energy productions are between October to March. PV power production is problematic during June and July. Power production is 1/8 of the average during those times. Excess generation is created and sold at a rate of 8 cents per kilowatt. Its peak sales back is in December at 38,000 kilowatt hours sold back. The ventilation load accounts for the largest heat load. By adding CO2 occupancy sensors to the spaces, minimum ventilation requirements for people drop significantly. The rainwater storage system was analyzed per owner's request. More than 600,000 gallons of water can be harvested per year with the 43 inches of annual rain and 19,000 square foot roof. Only a 6,000 gallon storage tank is needed to offset the water consumed by the radiant floor heating system with VAV bypass. The large storage tank can be kept in the parking garage. An underground storage tank was not used because the construction cost to burrow into the rocky island is very costly. A water treatment system, piping, and water tank is needed at an initial cost of $4,500, and a payback period of 2.26 years is returned. The total annual life cycle water savings is $74,000. Energy recovery is not installed into the service stalls and parking garage because of polluted exhaust air leaking into the supply. If a tight construction can be made with no leakage, 30 MBH can be saved by adding an energy recovery wheel. Installing a 15 by 15 by 10 aquarium in the community room can reduce the carbon footprint of the HVAC system. 1.83 kilograms of CO2 can be fixed via cultivating 1 kilogram of microalgae. Enriched CO2 glue gas coming from the gas-powered HVAC equipment would be deposited from a duct into the aquarium where the gas will be dissolved into the water. The water tank would be placed directly under skylights for algae growth. 2 pumps would be required to pump ocean water in and out of the aquarium for pH control. Many steps were taken to approach net zero. Energy efficient and effective equipment was selected. All lighting was replaced with LED lighting. Combination of gas and electric boilers allowed PV cells to be integrated into HVAC system, improving PV power generation, implementing HVAC fault detection. This was a presentation from Cal Poly Pomona. Thank you for watching.